Hi everybody, welcome to topic number 29, complex numbers. In this video we're going to show you how to write square root of negative numbers in the form of BI, add and subtract complex numbers, multiply complex numbers, divide complex numbers, and raise I to different powers. The complex number system includes the roots of negative numbers and the set of real numbers as a subset. This number system allows us to solve equations such as x squared plus 1 equals 0 that otherwise have no real solutions. The set of complex numbers includes the imaginary unit. So if you've ever heard of imaginary numbers, that is big in form of complex numbers. One of the things that we know is that we have an imaginary unit, and an imaginary unit basically represents the square root of a negative number. Remember, to this point, we cannot take the square root of a negative number because there's no way to multiply two negatives. Now we're saying we can take the square root of a negative and just call it I. We'll also know that the I squared is just negative 1 because, again, if I take I and I go through and I do I squared, well, that's simply the square root of negative 1 times the square root of negative 1. And when you multiply a square root times itself, the square root simply goes away. So that makes sense there. So when I go through and I write things in I notation, I'm basically taking out the negative right away and I'm turning it into I. So when I look at the square root of negative 36, the negative comes on the outside and it now becomes I. And then I can take the square root of 36. We know the square root of 36 is just 6. So now this will simply be 6I. Again, take the negative out and call it I. In this case, square root of 5 won't break down any further because the only things that multiply to 5 are 5 and 1. So this would be as far as I can go with this. Now, don't worry about this negative here. We're taking the negative on the outside out, and we're calling it I, and we're leaving the inside as a positive 20. We know 20 will break down to 4 and 5. 5 is prime, and 4 will break down to 2 and 2. So 20 now becomes 2 square root of 5. On the outside, we already had the negative and the I. And typically, we like to place the I after the coefficients. So in this case, this would be my final answer, negative 2I square root of 5. The negative comes from the negative that was already on the outside, and the negative on the inside is what gives us the I on the outside. The product rule for radicals does not necessarily hold true for imaginary numbers. Therefore, to multiply square roots of negative numbers, first we must write each number in terms of I. So then we're going to take all of these and multiply it in terms of I, remembering our two true rules, that I is equal to the square root of negative 1, and that I squared is also equal to negative 1. So when I go here, I'm going to turn both of these into I values. So I square root of 3 times I square root of 5. And then I can multiply these. I times I would give me I squared. Square root of 3 times square root of 5 would give me square root of 15. But now we know I squared would become negative 1. Negative 1 times square root of 15 would just be negative 1 square root of 15. Again, we take the negatives out first and turn them into i's. So this is I square root of 36 times I square root of 1. The square root of 36 is 6, so this becomes 6i, and the square root of 1 becomes 1i. 6i times 1i, 6 times 1 is 6, and I times I is I squared. The I squared becomes negative 1. It takes its place, and now I have 6 times negative 1, which is negative 6. We can do the same with radicals here. So again, I'm going to take the square root of negative 125, take the negative out, have it become I. 125 is 5 and 25, and 25 is just 5 and 5. So I have a group of 5s. 1 will come out, and 1 will stay in. So now this is 5i square root of 5 over square root of 5. I have square root of 5s on both the top and the bottom, so it cancels and simply leaves me with 5i. So again, One of the big things, and we'll see this later on, is when we see this I squared, it's becoming -1 every single time. And then if it's written right next to something, it's becoming a multiplication of that. Now that we have practiced working with imaginary unit, we will formally define a complex number. A complex number is a number that can be written in the form of a plus bi, where a and b are real numbers. So again, when we go through and we write these things, this form is just telling us how we want to give our answer. A is always the real part of the answer, and b always has the imaginary. So here, for example, they have 3i. If your answer is 3i, we don't just call it 3i, we say 0 plus 3i. This 0 here means that there is no real part that's in front of it. So if I don't have a real part, I put it in as 0. If I do have a real part, we don't really need the imaginary part because that's what we've worked with before. But it's telling us here that now, if I have an imaginary part only, we have to put in 0. Otherwise, we put the real part first and we put the imaginary part second. Think of it like combining like terms. If we have 5 plus 2x, generally we like to write it as 2x plus 5, but now we're just going to put the 2x at the very end. Two complex numbers, a plus bi and c plus d are equal only if a is equal to c and b is equal to d. Thus, we can basically add and subtract complex numbers the exact same way we think of adding and subtracting like terms. So in this case, we're just going to go through and combine what's like. So here it wants me to do 2 plus -3. Well, 2 plus -3 is -1. And then 3i plus 2i. 3i plus 2i is 5i. We treat it like it's a like term and keep the I how it is. This is written a plus b format, where a is the real number, -1, and the 5 here is the b because it's attached to the imaginary. Here with this negative, we're going to distribute it in. The 5i doesn't change. The opposite of 1 is -1, and the opposite of -i is +i. 5i and I combine will keep the real part the same. 5i plus I is 6i. Again, we always want to write the real part first, which is why I'm leading with the -1. Here on this problem, the double negative will become positive. So this will be +6. -3 plus 6 is 3 minus 7i. So again, I wrote the real part first and then the imaginary part second. When we add or subtract complex numbers, it is virtually the same as combining like terms. Multiplying is the same. When we multiply with i's, it's like multiplying with variables. When we did x times x, it became x squared. So I times I is going to become I squared. But again, the big part here is we have our I squared rule. I squared will always become -1. So we have to go through and change it to -1 every time we see it. Case in point here, -7i times 3i. -7 times 3 is -21, and I times I is I squared. But I squared simplifies to -1. And again, it's like -21 times I squared, so it's no different here. -21 times -1, which comes out to be +21. Here I'm going to distribute the 3i. 3i times 2 is 6i. 3i times -i is -3i squared. But again, just the I squared is going to become -1. We're not going to touch this I because it's only one I. This part becomes -1. I now have -3 times -1, so I have 6i plus 3, but we always write the real part first, so 3 plus 6i would be my final answer. Here we're going to go through and FOIL out. 2 times 4 is 8. 2 times I is 2i. -5 times 4 is -20i, and then -5i times I, negative times positive is negative, 5i times I is 5i squared. So now we've got two things we can do here. The first thing we can do is we can combine these like terms. They're both i's. 2i minus 20i is negative 18i. And then here we've got an I squared. That's going to turn into negative 1. Now I can go through and multiply this. So I have 8 minus 18i. Negative 5 times negative 1 is positive 5. And then 8 plus 5 gives me 13 minus 18i. The real part is first, the imaginary part is second. So this would be my final answer. Finally, for D, we can recognize these are conjugates. And we can use our same tricks we've always seen with conjugates. We're going to multiply the first by the first and the last by the last. 7 times 7 is 49. 3i times negative 3i, positive times a negative is negative. 3i times 3i is 9i squared. But again, I squared is going to become negative 1. So it's 49 minus 9 times negative 1. I'm going to multiply this as negative 9 times negative 1. So we have 49 plus 9, which comes out to 58. So again, a lot like multiplying with polynomials and our variables, but just remembering that when we get that I squared, we have to turn it into negative 1 and simplify it further. Again, we have the same thing here. If it's squared, we multiply it by itself. These are not conjugates, so we're going to multiply this out. 3 times 3 is 9. 3 times negative I is negative 3i. Negative I times 3 is negative 3i. And then negative I times negative I is positive I squared. Here this will combine, 9 minus 6i. And here the I squared becomes negative 1. And this is plus negative 1, so we can really rewrite this as a minus 1. 9 minus 1 gives me 8. So I have 8 minus 6i as our answer. Again, this is left in the form of the real first and the imaginary part second. Just like we did with rationalizing, we can rationalize it here. We do not want to leave an imaginary in the bottom. So in order to do that, we use the conjugate to get rid of it. And we'll use the conjugate of the denominator. So for this problem here, I'm going to multiply everything by 1 plus I. So at the top here, 1 plus I. So here at the top, we'll FOIL this out. 2 times 1 is 2. 2 times I is 2i. I times 1 is 1i. And I times I is I squared. And at the bottom, these are conjugates. So we'll do our conjugate multiplication. 1 times 1 is 1. Negative I times I is negative I squared. At the top, we have 2. These combine to make 3i. And the positive I squared will become negative 1. And at the bottom, this I squared will become negative 1. We still have a minus sign here, which is why I have this minus here. The double negative makes this a positive. So 1 plus 1. We'll still keep the top the same for now. Here at the top, 2 minus 1 gives me 1. So 1 plus 3i. 1 plus 1 is 2. So we can leave our answer like that. We could also separate it and say our answer is 1/2 plus 3i over 2 if we want to do the real part first and the imaginary part second. Here again, it's one term, so I'm going to multiply everything by 3i. At the top, this becomes 21i. And at the bottom, this is 9i squared. But the I squared becomes negative 1. So now I have 21i over negative 9. Both of these are divisible by 3. So this will become negative 7i over 3. Again, make sure you're changing that I squared into negative 1 every single time. We can also use the fact that I squared is negative 1 to find higher powers of I. So if we know I squared is negative 1, then I cubed has to be negative I, because negative 1 times I is negative I. And I to the fourth is just I squared twice. So negative 1 times negative 1 is 1. And then if you notice, once I get back to I5, I start to repeat again. All of these go in loops of 4. So that makes it really easy to find higher powers. We basically have to see how much it goes into. So what I would do for 20 is I would ask, how many times does 20 go into 4? In this case, it goes in 5 full times with a remainder of 0. So 1, 2, 3, 4, 5 times. We would end up in the last one. It would have no remainder. So my answer here is that it has to equal 1. So essentially, if I have a remainder of 1, it's I. If I have a remainder of 2, it's negative 1. If I have a remainder of 3, it's negative I. And if I have a remainder of 0, it's 1, because 4 goes into 4 one time with no remainder. Let's try it with 46. 46 divided by 4. 46 can go in evenly 11 times. 11 times 4 is 44, so I have a remainder of 2. A remainder of 2 is the same as I squared, which is negative 1. So I to the 46 is really I squared, which is simply negative 1. And again, you could try it with any of these numbers. If I gave you I to the 99th, 99 divided by 4, it goes evenly in there 24 times. 24 times 4 is 96, so we have a remainder of 3. So I to the 99th is the same as I to the third, which is simply negative I. Same thing here, just remember with a negative 1, we just bring it down to the bottom, so it's really 1 over I to the 24th. 24 divided by 4 is 6 with no remainder. So no remainder means it becomes 1, and 1 divided by 1 is 1. So we use sort of this pattern here to evaluate higher I powers as we do this.